I am Alden Wright, University of Montana, talking about evolvability and complexity properties of genotype-phenotype maps. And this is joint work with Cheyenne, Laue, also of University of Montana. And our objectives here are to better understand both computational and biological genotype-phenotype maps. The properties that we're concerned with include redundancy, meaning many genotypes per phenotype, robustness, evolvability, and complexity. So for us, genotypes are logic gate circuits as illustrated on the upper right. And these are highly heterogeneously redundant. We computed the plot on the lower right by sampling 10 to the 10th random circuits and counting how many phenotypes found. So the redundancy varies by at least 9 orders of magnitude. So what do we mean by phenotypes here? Phenotype is the Boolean function computed by the circuit over all possible combinations of inputs. So in the table, we have one column for each combination of inputs, and we compute the output of the circuit for each of those columns. And the bottom row, the result is the phenotype, which will represent as hexadecimal, in this case 0xa. And these can be computed extremely efficiently by bitwise parallel computation. So mutations are according to the Cartesian representation. Mutations can be changing a gate, say from AND to XOR, changing a link. These are point mutations. And so what do we mean by robustness and evolvability? So we'll start with genotype robustness, which is the fraction of mutations that don't change the phenotype. In the example circuit on the upper right, there are 14 possible mutations, and 2 of these mutations don't change the phenotype. So that says that the robustness is 2 out of 14. The evolvability is the fraction of mutations that map to distinct phenotypes. And in that list of mutation phenotypes for mutation, there are 9 unique phenotypes. So the circuit evolvability is 9 out of 14. So genotype networks, nodes are genotypes, edges are point mutations, and so each genotype or phenotype has a network of a subnetwork of this network where the nodes for that phenotype are collected by neutral mutation. And a remark that for our parameter settings, phenotype networks are almost always connected. Phenotype evolvability. So we're more concerned about phenotype evolvability than genotype evolvability. And so what do we mean by this? The phenotype neighborhood of a given phenotype P is a collection of phenotypes, one mutation away from a circuit implementing P. So the evolvability, phenotype evolvability, is the number of unique phenotypes in this neighborhood. And this measures the effectiveness of neutral evolution. How many unique phenotypes can you discover by sampling random phenotypes? So phenotype evolvability cannot be computed exactly in any realistic case, so it must be done by sampling. And we explore two methods of doing this. One is to evolve circuits that map to the given phenotype. The other is just to take a very large sample of genotypes and then only use those that map to the given phenotype. And that second technique is based on paper by Hu et al. In 2020. So looking at the example on the right, thinking of the blue 0xa phenotype, we count the number of adjacent different phenotypes, which are orange, dark orange, light green, and dark green, but not light blue. So counting the blue itself, there are 7 such phenotypes. So the evolvability of that shown phenotype network or phenotype is 7, much greater in any realistic case. So neutral evolution is a way to explore the genotype network or the phenotype network, starting with a genotype that maps to a given phenotype, like the blue node in the middle. We do a mutation. If this mutation is to a different phenotype, we might record it, but we discard it for the purposes of evolution, do another mutation. If that mutation gives the same phenotype, then that becomes the current mutation, and that's how we make evolutionary progress. And in most cases, one can explore widely for the genotype network, and it's a method, one method of computing phenotype evolvability. So evolvability versus robustness. So we started this project by looking at biological genotype-phenotype maps. Biologists discovered what they call universal properties, including a negative relationship between genotype evolvability and robustness, and a positive relationship between phenotype evolvability and robustness. For sampling evolvability, we found the same relationships, but for evolution evolvability, we found the opposite relationship for evolution evolvability. And this is key to our further results. So evolvability versus complexity, looking at, again, sampling evolvability versus evolution evolvability changes the relationship with complexity. Now, what do we mean by complexity? The complexity of a phenotype is the minimum number of gates needed to implement that phenotype. So that's is a direct application of Kolmogorov complexity. And so complexity is positively related to evolution evolvability, but not sampling evolvability. And we'll show in a minute how the evolution of complex goals enables the discovery of further complex goals. So this will demonstrate this here. We're supporting the arrow of complexity hypothesis, which is that increasing maximum complexity is an inherent property of evolution. This is maximum, not average complexity. So looking at the upper plot on the right shows if you take a random genotype, it is likely to have complexity between 2 and 5. But if you take a random phenotype, it is likely to have complexity between 5 and 10, much higher random complexity. So in order to evolve complexity, any complexity that's discovered must be adaptive in order to be maintained by evolution. So we set up random phenotype niches that we make adaptive. And so most of those random niches will be more complex, but not all. So then we start evolution, and evolution from a random genotype will start by discovering the less complex of these niches. But then when they're discovered, we eliminate them for further evolution, but use them as starting point for evolving additional niches. And the plot on the right shows that this process where we ratchet up from low complexity to high complexity is very effective. And so in our case, we set up these random niches for 4 input, 1 output goals, 600 out of the 65,000 possible phenotypes, and this process enables us to discover almost all of those 600. So our conclusions first is that neutral evolution is an effective strategy for exploring the innovation properties of a genotype-phenotype map. So this confirms similar biological results, and this is especially important in a changing environment where new adaptive phenotypes need to be discovered to maintain adaptation. And biological researchers have claimed that low redundancy phenotypes are unimportant because they're so infrequent they won't be discovered. But we show this is not true by showing that these low redundancy genotypes, at least for our circuits, are the high complexity genotypes or phenotypes. And high complexity is important for the progress of overall evolution and hypotheses like the arrow of complexity hypothesis. So our positive relationship between complexity and evolution enables us to evolve increasing complexity. Thank you.